Welcome everybody to chapter 8 of MCAT General Chemistry. Today is about gases, right? So ideal, real gas, and just gas laws, gas constants, all of those. So first, let's make something clear, okay? There's two things that we see. We see standard temperature and pressure and standard conditions. These are not the same thing, and you have to make sure you don't mix these up. So STP, standard temperature and pressure, is normally 0 degrees Celsius, which is also 273 Kelvin, and then 1 ATM, which is just a measure of pressure. ATM is atmosphere, so it's a unit for pressure. Cool. Now, standard conditions is going to be, anybody know, we see this a lot with our experimental passages. There's this really common Celsius temperature or Kelvin temperature that they like to throw at us. So what were we saying? Yes, 25 degrees Celsius. And then this is going to be 298 Kelvin. For anyone who doesn't know, all you have to do to convert from Celsius to Kelvin is you add 273, right? So 273 plus 0 is 273. 273 plus 25 is 298. And then this is also going to be 1 ATM. So the only real difference here is just the temperature. But I bring this up because a lot of times people think STP is 25 Celsius or 298 Kelvin, but no, that's standard conditions. The actual standard temperature and pressure is 0 and 1. Also, ATM, this is 1 unit for pressure. There's multiple different ones. So we have, 1 ATM equals 760 mmHg, I think millimeters of mercury. This equals 760 torr, this is another unit, and then 101,003, 50 something, right, of pascals. Or we can make this easier and say 101.3 kilopascals. So make sure you know these conversions, because yes, most of the time you see ATM, but every now and then they'll throw up millimeters of mercury at you, or even pascals. Okay, so now we have something called ideal gases. Ideal gases, there's different things that make them ideal. So one is that they have perfectly elastic collisions. So when I hear this, I think of bumper cars. Think about bumper cars coming together, and they I don't know what's it called, come together, and then they bounce exactly the same way apart. So what this actually means is when gases interact, they're not going to lose any energy at all, okay? They maybe use some energy to come together, and then they come out with the same energy. No energy lost. That's what elastic means. Whatever comes in, comes out, okay? There's no intermolecular forces between gas molecules. This means you can either attract or repel gases in reality, but ideally we're thinking that they don't have any of those attractions or repulsions, because when we talk about the equation for ideal gases, it involves pressure, and attraction and repulsion can affect pressure, and that's just too much to deal with. So in an ideal scenario, we're assuming that there's no intermolecular forces between them.
Wait, could you explain the elastic collisions one again?
Yeah, so, okay, here. So you have a gas, and it interacts with this one, right? Let's say I don't know, there was 3 joules for them to come together. They interact with 3 joules, and then when they end up bouncing apart, they're gonna bounce apart, okay? When they end up bouncing apart, none of this energy was lost. There's still 3 joules of energy maintained. Does that make sense?
Kind of.
Okay. Just think about no energy loss, right? You don't want there to be any energy loss, otherwise it messes up our calculations, which you'll see in the equation that I'm gonna bring up. But it just has to do with no energy loss. So a bumper car, right? Bumping into another bumper car, they come in like this at 2 miles an hour, and they come out 2 miles an hour. If you put glue on the bumper car, Now it's like interacts and then it kind of stops and slows down like 0.5 miles per hour. That's like some energy loss, right? So think about this like whatever it comes in with, it goes out with. The exact same. There's nothing, no energy, none of that is lost.
So it's like the forces are kind of like conserved, basically.
Yes.
Kind of how like for like chemical reactions, like your mass must be conserved or something like
Yeah,
that.
it's just conservation of energy.
Yeah.
But conservation of energy still means that like you can have energy loss. So this is saying that there's no energy loss. You
okay.
came in with 3 joules of energy and then you come out with 3 joules of energy. Like, okay, energy loss is kind of like you came in with 3 joules and then maybe you lost like 2 joules of energy as heat and then you just go out with 1 joules. But this is saying that you come in with 3 and you go out as 3. There's no energy loss between the molecules. Third one is gases. They occupy a negligible space. So this is saying like if we have a container and there's like, I don't know, 5 moles of this small gas versus 5 moles of a comparatively larger gas. Yes, okay, like this one will obviously take up less space and this one takes up more space. But we're just assuming that the gas molecules themselves, regardless of their size, they're not going to make a difference to the volume. So like, let's say the volume refers to like the spread of the molecules, right? So if you have a gas molecule spread like, you know, in like 5 liters and same over here, technically there's more volume here because the gases do really have volume, but we're assuming that there's no significant changes in volume. So they occupy negligible space. That's what we refer to that as. And then the fourth one is that gases, they're like constantly moving randomly. So random motion. And then we, okay, what's the big equation? Very, very common equation.
Pivnert.
Yeah, Pivnert. It's P V equals nRT. So P is pressure. It's supposed to be an ATM, okay? So if you're given like torrs or millimeters of mercury, then convert to ATM. So I'm gonna put different colors. ATM. Volume in liters. N is number of moles. And then T is temperature in Kelvin. Now R is a gas constant. There's 2 values of R's we see. We see R equals 8.314 and then R equals 0.08, I forgot the rest, 2 something. Which one is the right one for Pivnert? Don't get this confused because obviously they're different numbers, right? So you don't want to mess up your calculations. Anybody know which one we use for this and what the other one is used for? Wait, say that again? Yeah, so we're gonna use this bottom one, okay? Because the actual units for this, it's like liters times ATM over mole K. I think it's something like this. Whereas this 8.314, I don't remember the exact units, but it involves joules times some other stuff. So this 8.314, you're gonna see it with, you guys know this, delta G equals negative RT ln K. Is this joules over, I think it's like joules over Kelvin. So this 8.314, right? The 8 is used for like energy things, but the 0.08 is used for gases, okay? LATM, mole, and K. And yes, they're most likely not going to tell you the R value, so make sure you're fully aware of which one you're using in which scenario or which equation. Here, let me write that out. Joules per mole times K. But the main thing is it involves joules, whereas this one involves like pressure and like liters, okay? So using this equation, let's do a quick practice problem. All right, here you go. What is the volume of 2 moles of an ideal gas at 2280 torr and 27 Celsius? I'm gonna give you all like a minute for this one. Okay, so you know you got your PV equals nRT here. You're just plugging stuff in, right? So what is your P? Pressure 2280 torr, but it has to be an ATM. So I made it really simple. Like it's just a straight like what's it called? A whole number. Like 2280 divided by 760 will give you just straight up 3, right? So you're gonna have 3 ATM as your P. I'll put 3 right here. And then you're looking for the volume, so I'm gonna put V right here. And then N is 2 moles. R is 0.08. It's 0.082, but I'm putting 0.08 because you're estimating. And then what is our temperature? 27. Oh, it's 300 Kelvin because this is 27 Celsius, so 27 plus 273 is 300. And then you just figure this out. So it's like, so you get like 3V equals 48 and then V equals 16. What's the unit for this?
Liters?
Yeah, it's just liters. Well, yeah, make sure you're consistent with your units, right? We need ATM, not torr. We need Kelvin, not Celsius. And then liters, right? That's like the SI unit. All right, this was pretty simple, right? But let me give you all another question. Okay. What is the density of nitrogen gas at 4 ATM and 350 Kelvin? So this one is a little bit weird, right? Why are we asking about density? This formula PV equals nRT doesn't have density. We just have pressure, volume, moles, temperature, right? What even is density? What is density? The unit for it? Or like, what is it a measure of? It's gonna be mass over volume. But what do we have? We have number of moles. Where is the mass in this question? So let's write this out again. PV equals nRT. What is N? N is number of moles. What's another way we can write number of moles? Mass over molar mass. Because mass is going to be grams, right? And then molar mass is grams per mole. So if you're doing grams divided by grams per mole, it's grams times mole over grams. You get rid of this and you get moles. And so, you know, moles is number of moles. So you can replace the N with this right here. I'm put MW for molar mass or molar weight. Now, we still need density, right? So we have to bring V to the other side. So let's do this. P equals MRT over V MW. There we go. M over V is your density, right? So now you can simplify this even more. P equals, can you all see the difference between my P and this right here? Because this is supposed to be the Greek letter rho, which is how we actually write density. So this is my density, the rho, and this is my actual P. I have like a circular P right here. This is not really circular. So anyways, this is density. And then everything else, right? RT over molar mass or molecular weight. And then you're just like, from here you have the formula, so you're just putting it together. So we got 4 equals density times 0.08 and 350 over. What is the molecular weight or molar mass of nitrogen gas?
28.
Yes, 28. So nitrogen, if you look at your periodic table, it's 14, but nitrogen is a diatomic element. I'll talk about diatomic elements after, but it's going to show up as N2, not just N, so N2. So if n is 14, then times 2, you have 28. All right, so we got 28 over here. And then, yeah, this is just algebra. Like, I just be moving it around and stuff. Like, you're trying to isolate this row. So let me solve this real quick. So your density is 4, and then what's the units for this?
Grams per liter.
Yes, grams per liter.
So, when do you know like when to use like N, like the molar mass of nitrogen alone versus so anytime it says gas, it's automatically if it mentions gas and it's a diatomic, then you have to use like the diatomic version, like the diatomic molar mass.
Yeah. So let me elaborate on this. First of all, everyone good with this? Or I mean, I'm gonna get rid of this one actually. I'm gonna get rid of this. So yeah, let me first mention what diatomic elements are, and then I'll get to that. So diatomic, right? Diatomic, diatom means 2 atoms. So there's like a few elements that are always going to be diatomic, like in nature. Anybody anybody know the diatomic elements, and like how do you remember? Because the way I remember is Brinkel-Hoff, but I don't know if that's like a common thing. What do you use?
Have no fear.
I knew it, but
of ice cold beer.
So okay, I use something called Brinkel-Hoff. So it's like BR2. Actually, they're all gonna have 2s, right? But here. No, we just have no fear of ice. Yeah, I guess that works. So these are your diatomic elements. They all have 2. So if you're talking about like fluorine gas, it's just F2 gas. You're talking about oxygen in the air, we talk about it as O2. In this case, nitrogen gas, N2, okay? So if you get a question like this, density of nitrogen gas, just assume it's diatomic, unless they specify density of monoatomic nitrogen gas. But if they don't specify monoatomic, which means just 1, you're just gonna assume that it's diatomic because that's what it's normally found like in nature.
So, for example, if they mention something like, let's just say 1 mole of hydrogen,
Yeah.
right? Not in the context of like gases, but just in general, like in Gen Chem, right? For some Gen Chem question. So, if it says like 1 mole of hydrogen, are we supposed to assume that it's hydrogen by itself with a molar mass of like 1 gram per mole, or is it going to be H2, so 2 grams per mole?
Okay, usually this diatomic stuff, it's more like common for gases. So if they said the, were you asking moles? Remember moles? What were you saying?
No, if they just say like 1 mole of hydrogen, like, are we just supposed to, like,
you asked about mole? Okay,
regardless
I was asking,
of the gas phase, just in general?
Okay, I got you. Now I was asking what unit you were asking about. Yeah, if they say 1 mole of hydrogen, that's it, then they're most likely referring to just hydrogen, just 1 H. But if they specify hydrogen gas, then that's gonna 100% be H2.
Okay.
I don't think they'll make it confusing like that, where they just say hydrogen. But generally, if they just say hydrogen, they're not referring to the diatomic stuff. These are mainly for like gaseous forms. All right. So we have our PV equals nRT, right? Really briefly, I'm gonna cover this one thing called the Boltzmann constant. So this right here, all this is telling you is this is kinetic energy and this is temperature, and then this Kb is a constant, and then there's like a 1.5, right, 3/2, like constant there. So Boltzmann constant just relates the kinetic energy to temperature of ideal gases. That's kind of all you have to know. I don't even think I've seen a question like this. If you did get a question, I guess know this formula, but it's pretty straightforward. You just plug in, like, use those. units. But the main thing to know is that the Boltzmann constant relates the kinetic energy to temperature of the gas. And this tells you like as temperature increases, the kinetic energy will increase. Now for this PIV, this PV equals nRT, there's different laws, right? So let's write some of them. Let me erase this. By the way, this ideal gases, these like 4 things that I wrote, real gases, like non-ideal gases, are just gonna be opposite of these, right? So real gases are not gonna be perfectly elastic. They're going to have some energy loss when they interact. Real gases actually have intermolecular forces when they collide. And real gases actually occupy some space, and then they don't necessarily move randomly. Like there's definitely some order in their motions.
And are those like for ideal? It's like some sort of
The high
pressure
temperature?
involved? Yeah.
Yeah. I was thinking about when to mention that. I think I'll just mention it now. So, ideal gas, if it tells you it's an ideal gas, it's ideal, okay? If it tells you it's a real gas, it's a real gas. But there are like times where gases, even if they're real, they can act ideally. And there are times where these real gases will just act like real gases, like non-ideal. So I'll put act like ideal. So for acting like ideal, the conditions are high temperature and low pressure. And then for non-ideal, it's just the opposite, low temp and then high pressure. Do you know why? Yeah, what's up? Wait, can you speak louder, bro? Okay. Yeah, kind of. So like, look at this, right? Temperature, when temperature is high, what did we just talk about? The kinetic energy is high. So particles, gas molecules are moving a lot, and there's all this motion going on. And so if they, if they're moving a lot, then like think of your container. These gas molecules are just moving around. They're like hitting the walls a lot. So that's maintaining a pressure, right? If you, if you decrease pressure, then the molecules are not going to like be that far apart. They're gonna be more close together. And when your molecules are really close together and they're interacting, then you can't just say, okay, they don't have any important or significant forces between each other. At some point, if they're really close enough and they're constantly close together, they're going to have significant interactions. Wait, fuck, I just messed that up. I'm so sorry. That's if you have high pressure. Low pressure means that the molecules are not close together. They're not like, think about high pressure, like really compact, okay? Low pressure means they're spread out. They're spread out like this and they're not really close together. What I was talking about was high pressure. If you have high pressure, they're close together and their interactions are significant. And then same with low temperature. If your temperature is low, there's low kinetic energy, so you're not moving around that much. You're not maintaining like a pressure on the outside, and you're just like, your interactions are more significant there as well. So just, you're not gonna really get a question where it asks to determine like what is considered high pressure or low pressure, high temperature, low pressure, but just know like what will high temperature, low pressure do? It's gonna make your gases act more ideally, and if it's the opposite, it'll make it act non-ideally. Okay, so there's 4 laws that are like based off of this PIV, and it gets a little like confusing. So let me write them out, and then I'll explain like the really easy way to remember them. So with this PIV thing, if your pressure increases, then something on this side will increase, right? So pressure and temperature, for example, they're directly related, they're directly proportional because they're on opposite sides. But look over here, right? If your pressure increases, then and this stays constant, then your volume has to decrease, because if they're on the same side of an equation, they're inversely proportional or inversely related. So that's where we get these from. Like this first one, Charles' law, is volume over temperature. They're on opposite sides. We use a dividing to show that they're directly related. And then if they're on the same side, then we're gonna put it like this, like PV equals PV, right? So these are the laws, right? Charles, Gay-Lussac, Boyle, and Avogadro. And then I think like for one of them, like Avogadro, it's N1 over V1 equals N2 over V2, but it doesn't matter because the proportionality is still there. So how do I remember this? Okay, I found this mnemonic on Reddit. Can girls be actual virgins to please Victor's neighbor? Very, very funny, right? So let me explain how this works. If you say this a lot, then you're gonna like at least like somehow remember it. Like this is stuck in my head. So here's what you have to look at. This can girls be actual. These C, G, B, and A, this is where I got this from. Charles' law, Gay-Lussac, Boyle, and Avogadro, okay? Now from here, it's a little weird, but you'll get used to how to use this mnemonic. This first one, this Charles' law, is gonna correspond to these two, virgins two, so V and T. That's where I got this V1 over T1 equals V2 over T2, okay? Now the second one, girls, the Gay-Lussacs, is gonna shift one to the right. So it's gonna be two please. Are you guys following along? I'm gonna number this as 1, 2, 3, and 4. Let me know if you're not following along. So yeah, Gay-Lussac is gonna be 2 please. So TP, this is temperature over pressure equals temperature over pressure 2. And then this one, this Boyle's law, is gonna continue. So PV, please Victor's, and then Victor's neighbor for 4, okay? So that's where you got the PV and then V over N. As for, once again, remembering like if it's dividing or multiplying, just look at your Pivnert. This will tell you everything you need to know if you forgot. But as you can see, all of them are dividing except this one, it's the multiplication one. And so if you look at like a graph, right? The graph for all the dividing ones is just gonna be like a linear thing like this, right? So let's put V over here and T. Same thing over here, if I put T and P, it's gonna be linear. And this last one, linear. Now for this P1, V1, P2, V2, the graph is gonna look like this. Like a, what do you call it, hyperbolic curve. And this graph is pretty important. We're gonna use it more in the thermochemistry chapter. We talk about like adiabatic, isobaric processes, isochoric, all of those. So just kind of like remember this graph, but it's fine if you don't remember, I'll bring it up later on when we get to that chapter. So how is this mnemonic, like, are you guys like it or not? Cause like, I don't really know any other way to even know this unless you just straight up memorize this.
It makes a lot of sense.
Yeah, it's like, bro, Reddit comes clutch, like very, very clutch sometimes. And then if there's something called the combined gas law. So I'll put combined gas law. I never encountered them asking what the combined gas law is. It's gonna be this right here. So you're combining like this Boyle's law with like Charles' law or even this one. So PV over T. But these are really helpful because they'll like tell you like, okay, pressure and volume stayed constant, but then temperature increased to like 500 Kelvin. So what is the new pressure or something, right? So if you like, here's what I'm trying to say. You don't need these to solve a question like that, right? You just need this Pivnert to determine the changes. But as I mentioned in chapter 1 of general chemistry, you should know these by name because you never know when they'll just throw a question at you asking what law is represented by volume and temperature correlation, right? And the last thing you want is to like get that shit wrong because you didn't know. And same with like laws, right? Like thermodynamic laws, Newton laws. Know exactly like what they are, these names, know what they mean, what they refer to. Do you guys like this one? Do you understand this mnemonic?
Can girls be actual virgins? margins to please Victor's neighbor. Oh, Charles gave Blue 6 boiled Avogadro. Oh, okay.
So these are like the ideal gas law derived laws. There's more gas laws, but they're not like based off of the Pivnert. So Dalton's law is gonna tell us that you've all heard of like partial pressure, right? Partial pressure is like the partial pressure, right? You have a total pressure, and then some gases will have the partial pressure of that, right? Like I don't want to use the word to define it. Some gases will contribute partially to the total pressure, right? So we show this as this. PT is total pressure, and then let's say you have like 3 gases, right? Gas A, gas B, and gas C. Each of these is gonna have a partial pressure. When you combine the partial pressures, you get the total pressure. And if you're wondering if this refers to ideal or real gas, I think all of these things can refer to real gases to an extent, but we mainly deal with ideal gases for the laws that, oh, obviously these, right? These are ideal gas laws. But this one and the next one I'm gonna mention. Yeah, but there's not gonna be anything confusing. So like, you can also determine a partial pressure using mole fractions, right? So let's say I want to figure out the partial pressure of A. I need the mole fraction of A times the total pressure. What is mole fraction? Let me get another color. If I have like 3 moles, I'm sorry, I always ask it, but can you see the end on this? Okay. We have 3 moles of A, 4 moles of gas B, and 5 moles of gas C. What is the, X is the mole fraction, okay? What is the mole fraction of gas A? It's just the amount that's there overall, right? Compared to everything. So there's 3 moles of A over what's the total number of moles? It's 3 plus 4 plus 5, which is 12. 12 mole total. So the fraction here is 1/4. Gas A just takes up like 1/4 of the total, container, and the other 3/4 come from B and C. So if your total pressure in the system was like 30 atm, what is your partial pressure of A? Based on what we just like determined, 1/4. It takes up 1/4 of the container, and the container has a pressure of 30 atm. So A is just going to have or contribute 7.5 atm. And once again, yes, this is the pressure of A, but it's the partial pressure overall because the overall container has pressures from multiple different gases, not just A. Okay, I have a question, but it's for the next law. Yeah, okay. So now we have something called Henry's law. This one, I don't know why, I always like forget this one. So, for this one, actually it's a P. This is like referring to, what do the brackets mean? It's like concentration, right? Concentration, this KH is a Henry constant, and then P is partial pressure of A. So like, let me just give a question and it'll be easier to explain. How do you find a Henry constant? You just rearrange this stuff, right? So you're gonna do, concentration of A over partial pressure of A. And this is like important to know because the Henry constant for a given gas is just going to be the same. It's a constant. And so if your like concentration like increased by like 100,000, then you can figure out the new like partial pressure based off of the constant that you're given. So like, here, let me make this make more sense. From this, you can get this, right? Because in both cases, the Henry constant will be the same. So you want these to equal up so that the Henry constant will be the same. Actually, I'm around the other side, so y'all don't have the law to look at. If 3 times 10 to the this is 10 to the negative fourth moles of oxygen gas are dissolved in 1.5 liters of solution at 3 atm. This is asking what is its M means like molarity. I just wrote capital M, but what is its molarity if pressure increases to 12 atm? Sergio, would you like to solve this one? Anybody else want to solve this? But y'all are mad quiet. The front is always loud, but y'all are so quiet. All right, so this is like a, what's it called? It's a Henry constant question. So what was the equation? It's concentration of A, gas A equals Henry constant times partial pressure of A. And then we move this around. We got KH equals solubility or concentration of A over PA. And then you can compare two different scenarios just doing this, right? A1 over PA1 equals A2 over PA2. So we're given the stuff, but not like fully there, right? What is molarity? What is the units for molarity?
Moles over liters.
Yes, moles over liters. So we have to calculate that because we're just given moles and liters. And so you got 3 times 10 to the negative fourth mole over 1.5 liters of solution. And this is just 2 times 10 to the negative fourth, capital M, which is moles over liter. And so this is occurring at 3 atm. So that's just like, it doesn't tell us anything else. So we're just going to use that as the partial pressure of A in this case. So we have this over 3 atm. And this is going to equal A2, or concentration of A2 over PA2. We're given PA2, which is 12 atm. And then we're just looking for this. So you can either like cross multiply, or you can just look at this, right? How did I get from 3 to 12? I multiplied by 4. And these are directly proportional. Are they directly or indirectly proportional?
Which one?
These two. They're being divided, or are they directly or indirectly?
Indirect.
No, they're directly proportional.
direct.
If we're dividing.
Right.
Yeah, so what you can do is you see from 3 to 12, I multiplied by 4. So I'm just going to multiply this top by 4 to get the new solubility or concentration. And so that's just 2 times 4 is 8, right? Times 10 to the negative 4th molar. And this is your A. So that's like a type of question where I'd see this Henry constant being useful. Just know this formula and then this like comparison right here. Everything else, as far as I'm aware, not that deep. This is like a low yield law, in my opinion. But I have seen it show up, right? But it's just these scenarios where it shows up. Okay, now.
Sorry, where's
Yeah.
the 2? Can you explain the 2 times 10 to the negative 4 again?
Yeah. So this is concentration, which is molarity or moles over liters, and this is moles and liters. So we need to find out the molarity. So you're just dividing moles by liters, so 3 over 1.5.
Oh.
And 3 over 1.5 is
Yeah.
2. Yeah.
Oh, okay.
MVMT means movement. So things that affect gas movement, temperature, and molar mass. So temperature, we already talked about. If you increase temperature, then your kinetic energy is higher. So high T equals high, right? If there's high temperature, high kinetic energy, lots of energy. What does kinetic mean? Like movement. So high energy for kinetics lots of movement, right? That's good. Molar mass. If your mass is high, think about like people racing, right? The smaller, skinnier people generally run faster than the big, fat, obese people, right? So if your molar mass is high, this is going to be a low like speed or low movement. Another way you can remember this is little guys move faster. I just always remember this one, but it just makes sense, right? Small things like the example I was using, the race, like you just move faster. So there's less of you to move, whereas big people, there's more of you to move. So generally, these smaller ones move faster. And this applies to gases. And there's like a law that I guess proves this. I don't know if you say prove, but the law associated with this is Graham's law. And it will look like this. So this is rate of the gas 1, rate of gas 2, and then it's inversely proportional. So the molar mass of gas 2 and molar mass of 1. You don't have to know how to like solve this. This is just a law if you're like curious. I mean, okay, here, know what Graham's law refers to. Maybe know the equation. It's not really that hard, but know that Graham's law is referring to gas movement, right? And it just tells us that the lower the molar mass is, the faster it will move. The higher the molar mass, the slower it will move. Now, I just said the term gas movement. There's two terms that are related to movement. We have diffusion and effusion. What's diffusion? Someone tell me. This is something you should know for sure. You over there, answer this. You know what? How about you over there? Answer this question. No, not you. You guys always answer. Bro, it's so easy. What is diffusion? You tell me.
It's spreading from high to low.
Yeah, it's just movement of particles from high concentration to low concentration, right? So high, do this. This bracket means concentration. So high concentration to low concentration. So I have like all these particles here, and I have like one here. They're going to gradually move here so that they can be like the same, right? So that's just diffusion. It can apply to anything, like water, solutes, all that stuff. Effusion, it's not necessarily diffusion, but it's like movement of gas particles. So like the way I think about this is like gas like moving through like a small hole. And it's just, what's it called? It's like gas moving through this. That's just what effusion is. It's just movement of gas through like a small hole. And then the rate of effusion will just depend on if it's heavy or lightweight. So high molar mass or low molar mass. All right, any questions? Nothing to add?
Just to verify,
Yes.
molarity is basically like concentration, right? Just to remember.
Not basically concentration, it is concentration.
It is.
Yeah.
It is. Okay. Thank you.
Uh-huh.